Now we've already seen this, we've already done it, but we're going to do it again. We start with a delta x by delta y rectangle down in the xy plane. And that rectangle contains a sample point x star y star. Any old point in there, x star y star is okay. And what we're going to do with this is we're going to find the volume above this rectangle beneath this curve. Okay, this curve does lie above the rectangle as long as we don't go too far out in the x and y direction. When we put all this together to an integral, you know we're going to let everything, all our delta x's and delta y's go to 0, which means it doesn't matter where we put x star y star inside this rectangle. As long as it's inside the rectangle, what we get is going to be close enough as we take the limit and let delta x and delta y shrink to 0, because as delta x and delta y shrink to 0, this point has less and less room to wiggle around. Okay, there's less and less uncertainty just where that point might be. I'm not going to get into the details of that reasoning, but that's kind of the way it feels. Okay, so now we have this function z equals 100 minus 2x star, 100 minus 2x squared minus y squared. And we're going to assume that the point x star y star is located in part of the xy plane within the ellipse in the xy plane. For which this value is greater than 0. Okay, set this greater than 0, you get the equation of an ellipse. Okay, it's going to be an ellipse with a major axis in the x direction, square root of 50, and in the y direction, 10. Okay, so there's an ellipse down here. This is inside the ellipse so that the surface z equals f of xy, the graph of this function, lies above the axis. Okay, then we're going to ask ourselves, how far above the axis does the graph of z equals f of xy lie at this point? How do we get that? Well, z is how far it lies above, and if the point is x star y star, we're just going to evaluate this at x star y star, and that's going to tell us how far we got to go to get up to the z surface, the z equals f of xy surface. So how far is that going to be? Well, we evaluate this at x star y star, we get just this, but the x is going to be an x star, the y is going to be a y star. That's how high it's going to be. We're asking what the volume of the thing is. Well, the volume of the region above this rectangle and below the surface is going to be very close to, and I've got equals to, and I should make that approximately equal to. It's going to be approximately equal to, and if delta x and delta y are small enough, very close to this altitude at the x star y star point multiplied by delta x and delta y. It's just a rectangular region, a thin woodblock region. Okay, so there's our volume. Now, how do we get the total volume? Well, let's look in terms of this picture. Right here is a little rectangle. It's within a strip, and you should recognize what that is from earlier videos, but the strip has dimensions delta x, which is a distance from here to here, okay, the width of the strip, by delta y. It's also got the sample point x star y star. So this little square here, or rectangle, is our rectangle down here, and the question is, how much volume lies above this rectangle? Well, if z is in this direction, you get how far you got to go to get out to the surface, and that'll be the height of a rectangular solid whose volume is very close to the volume above this rectangle below the surface. And that's this rectangle. It lies directly above this. Now, if we take this whole strip of width delta x and partition it so that we have a bunch of little rectangles, okay, and then take limits as we've seen before, then we'll be essentially multiplying delta x by the integral of your y function, where your function f of xy is restricted to the plane where y equals y star. Now we've done that earlier, and I'm just invoking that. I'm not going to explain that here. It's been explained previously. But then we're going to have an integral from here to here multiplied by delta x, and that's going to be something that then we integrate with respect to x as we move from here to here and get the total volume. Now, bypassing the details of that process, which you should have seen by now, we see that the total volume is going to be the integral. Now I'm going to do the integral as, x is going to go from -2 to 2. Your values of x star all lie between -2 and 2, and they can be as close to -2 and 2 as, they will be as close to -2 and 2 as dictated by the width of delta x, which is going to approach 0. So the x integral goes from -2 to 2, and for each x between -2 and 2, we evaluate the integral of this function restricted to the y equals y star, or just to the vertical plane through coordinate y. And that's going to be this. Okay, well, that's a vague explanation. Hopefully you understand it in terms of the more complete explanations we've seen earlier. Bottom line, you take this description. X goes from -2 to 2. That's going to be your ultimate integral. And inside that, you have the integral where y goes from x squared to 8 minus x squared. And what are you going to integrate? You're going to integrate how high this thing rises. Okay? You're going to integrate the distance from the xy plane up to the surface, which is going to be this. Okay, well, the integral is easy to perform, so there it is. Now I actually work it out over here, but we'll save that for a minute. Once it's written down, it's easy to evaluate. In this case, it's easy because your functions are easily integrated. Sometimes the functions might be a little more complex, and sometimes they're not even integrable, and then you got to approximate. Okay, well, that's one way to set up an integral for the volume. The other way is to essentially integrate over this region here below y equals 4, and integrate over this region here above y equals 4. And for both of these regions, we have a good description. Okay, we integrate over both regions and add them up. Well, the integral over this part of the region, bounded by the two curves, goes from y equals 0 to 4. Okay, so we integrate with respect to y from 0 to 4, and then what does x do? We integrate with respect to x inside of that, and x goes from -square root of y to square root of y. Right there is this part of our integral. This part of our integral goes by this inequality. Y is greater than or equal to 4. It's also less than or equal to 8, because 8's as high as things go. So it's the integral from 4 to 8 of, with respect to y, okay, because it's y that goes from 4 to 8, and within that, x, for any y between 4 and 8, x goes from what? -square root of 8 minus y to +square root of 8 minus y. And I had y squared here because I wasn't thinking when I wrote it, so let's fix that. Square root of 8 minus y. A lot of times you'll have a y squared because we do a lot of stuff with ellipses and circles. Anyhow, it's -square root of 8 minus y to square root of 8 minus y. And you're still integrating. The height of this thing above this delta x, delta y interval is what it is. It doesn't depend on whether you're doing strips of little delta x squares or strips of little delta y squares. It doesn't matter which order you integrate, you're integrating the same function. So here is the integral as applied here. Okay. Then finally we do the integration, and I'll go over that real quickly. And then I'll talk a little bit about area.